our very idea of what a proton looks like has now shifted from a point particle to a three-part particle to a whirlwind of elementary particle activity. In fact, it is very difficult to distinguish between the disturbances that represent virtual particles and disturbances that represent actual particles in a plasma like this. But for our purposes, we can view a proton as a cloud of gluons holding three quarks together. The proton is key to helping us understand the origin of mass. The only stable elementary particles in the proton with mass are the two up quarks and one down quark. Their tiny masses constitute only 1% of the mass of the proton. 99% comes from the energy of the fields and motion of the moving parts following the famous E=mc² formula. So it is quite accurate to say that confined energy is the origin of mass. As the distance between quarks grows to the diameter of a proton, the strength of the force approaches 18 tons. Imagine 18 tons focused on such a tiny spot. This makes it virtually impossible to separate quarks. One last item on the strong force answers the question I raised at the end of our segment on the atom. What holds the protons together in the nucleus? In 1934, the Japanese physicist Hideki Yukawa made the earliest attempt to explain the nature of the nuclear force. According to his theory, a particle was being shared between nucleons like molecules share electrons between atoms to bind them together. Here's a two-proton example of how we think it works. First, in one of the protons, an energetic gluon spontaneously creates a down quark, anti-down quark pair. Next, the pion drifts into the other proton, and the anti-down quark annihilates a down quark, leaving the other down quark to take its place. The study of quarks, gluons, and their color charges is called quantum chromodynamics, or QCD for short. It is a very active area of research, and changes in our understanding are expected as we learn more.